sessions dealt with rational and irrational numbers, and we've been able to set a foundation to our understanding of rational and irrational numbers. I repeat, rational numbers would be those that could be expressed as a ratio of two integers, and in their lowest form, ratio of two integers that have only one as the common factor. And irrational numbers are those which cannot be expressed as ratio of two integers. The deployment towards establishing a number to be irrational is primarily the method of contradiction. We also looked into some of the properties of rational and irrational numbers, but then of course we can keep adding to our kitty those properties. We can go on endlessly, we can explore, evaluate, judge and obtain more and more properties, but some of the basic foundation has already been set. There are times when you would encounter a combination of numbers, say for example root 2 plus root 3, which is two irrational numbers, and like I told you in the previous session, sum of two irrational numbers can be rational as well as irrational, and therefore we cannot be conclusive. This is irrational, this is also irrational. So we cannot readily say whether it's rational or irrational. Hardly. It seems it's irrational. What we assume is, let's start by assuming that this is rational. Let's start by assuming that root 2 plus root 3 is rational. Let's start by assuming that this is rational. If it leads to a contradiction, then the assumption would be wrong, and root 2 plus root 3 would be deemed irrational if it leads to a contradiction. So if it's rational, let's say this rational number is r, where r could be expressed as a ratio of two integers, right? Now once I do this, then realize that I could get root 3 as r minus root 2, where r is a rational number. Now when I square this, then this is what transpires, right? This would then further lead to 3 equal to r squared minus 2r root 2 plus 2. And squaring, this is what I get, 3 equal to r squared minus 2r root 2 plus 2. Now, this would give me 2r root 2 on transposing as r squared minus 1. See, I transpose this here and transpose this here. Then 2r root 2 is r squared minus 1, etc. R then is, I'm so sorry, root 2 then turns out to be r squared minus 1 divided by 2r. That's root 2, r squared minus 1 divided by 2r, where r we assumed is rational. We assumed that r is rational. Now this basic premise of assuming r to be rational, what does it lead to? It leads to a statement which is root 2, which is an irrational number, is r squared minus 1 by 2r. Now, let's examine the right hand side. If r is rational, then r squared will also be rational. Why? Say if r is p by q, where p and q are integers, and q is not 0 of course, then r squared would be p squared by q squared. If p is an integer, p squared is an integer, q is an integer, q squared is an integer. So this is ratio of two integers. So r being a rational number, r squared is also forced to be rational. Now if r squared is rational, if you subtract this rational number from this rational number, if you subtract two rational numbers, r squared and 1, then what you get is still a rational number. So the numerator of this, r squared minus 1, is rational. Why? Because it's the difference of one irrational number and another rational number. One rational number and another rational number. The numerator is rational. Why? Because it's the difference of one rational number, r squared, and another rational number, which is 1. So difference of two rational numbers will be a rational number divided by 2 times a rational number. Now 2 times a rational number will also be a rational number, right? So which means the denominator of this is also rational. So it's ratio of 2 rational numbers. And ratio of 2 rational numbers, like we've commented before, will also be a rational number. Now, what's the issue with this? The right hand side is rational and the left hand side is irrational. What does it lead to? Irrational equal to irrational? Now, does it not sound irrational? It's bizarre. It leads to a contradiction. It leads to an irrational result. Irrational number equal to a rational number is just not possible. And therefore, the conclusion is the fact that there must be a problem with the original assumption. Since it's led to a contradiction, the contradiction is irrational equal to rational. That's a contradiction. That's a fallacy. The problem must be somewhere in the original or the mother assumption. The mother assumption that root 2 plus root 3 is a rational number must therefore be gross, incorrect, inept. Therefore, root 2 plus root 3 must really be not a rational number but must be an irrational number. And like I had said before, irrational plus irrational could be rational as well as irrational. In this case, it turns out to be irrational. In this case, it turns out to be irrational. Now, having said this, another very pertinent issue that I want to address is the following. Another remark that I want to make to you, and just keep this in mind, we'll very conclusively establish this later. If P is any prime number, then square root of P will always be irrational. We'll establish this later on, but for the time being, take cognizance of this fact. If P is any prime number, then square root of P will always be an irrational number. How? We still want a physical feel for these irrational numbers. No matter how irrational they are, no matter the fact that, we can't express them in terms of a decimal notation that would terminate or would be recurring. Can't give them a very proper decimal formation. Non-terminating, repeating is not occurring in an irrational number. We still want to be able to express irrational numbers geometrically. We want to locate irrational numbers on the real number line. That's what would give us a feel for their existence. Now, say for example, this is the real number line. Real number line. Now, on the real number line, as you already understand, there is 0. To the right of 0 would be all positive numbers. To the left of 0 would be all negative numbers. And I want to locate where root 2 lies on this real number line. What we do here is, we can locate the number 1. 1 unit away from the origin is the number 1, right? Now, this 1 unit, we drop a perpendicular of 1 unit length here. This 1 unit, I map it here. I draw a perpendicular of 1 unit length. This length is 1 unit as well, right? Let's say this is the point here, and this is the point here. Right? Then what, according to you, would be this length? Pythagoras theorem. This is 1, this is 1. So this is going to be root 1 square plus 1 square. Therefore, this is going to be square root of 2. OB turns out to be square root of 2. Now, what you do is, you take a compass, place it here, place the compass here, with this as the center and OB as the radius. With this as the center and OB as the radius, you draw a circular arc. With O as the center and OB as the radius, Draw a circular arc. The circular arc will have root 2 as its radius. Would have root 2 as its radius. So do you realize that OB will be the same as OC? OB will be the same as OC. Each will be equal to root 2 units. Right? So if OC is root 2, distance of O from the point C on the real number line is root 2, then what does C represent? C must represent the irrational number root 2. C must represent the irrational number root 2. And therefore, it's possible to express irrational numbers on the real number line. They do belong to the real number line. In fact, another fact that I want to mention, if you have any two rational numbers on the real number line, then between any two rational numbers P and Q, there would be an infinite number of rational numbers and there would be infinite number of irrational numbers. Please make a note of it. Between any two rational numbers, there would be infinity of rational as well as irrational numbers. Between any two rational numbers, there would be infinite number of rational numbers, there would be infinite number of irrational numbers between any two rational numbers on the real number line. This is a very important fact. Also, between any two irrational numbers, if you take any two irrational numbers, then also between those two distinct irrational numbers on the real number line, there would be infinity of rational and infinity of irrational numbers. Although, let me tell you, for the time being, I am just stating it frivolously, but a formal proof of this is pending. We'll go back and forth in our digressions. I'll give a very formal proof of this in times to come. But for the time being, this time of knowledge is pertinent and required. Now, like I said, and we established that root 2, which is an irrational number, could also be located on the real number line. Similarly, we could also locate root 3. Let's see how to locate root 3 on the real number line. Given that we can locate root 2, given that we are already able to locate root 2, see, this would be root 2. So OC would be root 2 units in length, right? OC would be root 2 units in length. What we do is, we drop a perpendicular on C, 1 unit long, CD. CD is 1 unit long, OC is root 2 units long, therefore OD would be what? OD would be, from Pythagoras theorem, root 2 square plus 1 square, which would be root 3. That's going to be OD. So with OD as the radius, and O as the center, we draw a circular arc which intersects the real number line at E. So do you realize that OD will be the same as OE? Each will be equal to the radius of the circle. So distance of E from the origin is root 3 units. Therefore, E represents the number root 3, which is another irrational number. So geometrically, it's possible for us to represent irrational numbers on the real number line very effectively and very conclusively. Now, this much for this session, and there is a world of things to explore about rational and irrational numbers, and that's there to follow in sessions to come. This much for this session.